Peiris, who is going to give this talk, which is a joint presentation with Nadia, who is also here. Good to see all of you. And Vinesha is a student, a PhD student at Swinburne University, unless I missed something and she has already got her degree, but I'm unaware of that. She will tell us if I'm wrong. And today she is going to talk about Chebyshev approximations, obviously, and specifically about rational Chebyshev approximations and how linear inequality method, probably she will remind us what it means, can be generalized. Okay, Vinesha, you were already recorded. I still remember, Matt, but okay, you did it well. Thank you. Vinesha, your time starts now, please.
Thanks, Alex. So hello, everyone. I am Vinesha Peiris. I am a second-year PhD student at Swinburne University of Technology. So today I will be talking about extending the linear inequality method for generalized rational Chebyshev approximations to approximation by general quasi-linear functions. So this is a joint work with Nadia Sukurukova. So since my topic is longer than usual, so I will break things down for you. So I will first talk about uniform approximations. So they are the approximations in uniform norm. And then linear inequality method, it is one of the oldest but yet simplest method developed for rational approximations in Chebyshev norm. And then we have the bisection method. It is developed for quasi-convex function. It is again one of the simplest methods developed for quasi-convex functions. So basically, I will be talking about the correspondence between the linear inequality method and this bisection method developed for rational approximation. So this is a new look on the linear inequality method from the point of view of quasi-convexity. And then finally, I will show you some interesting numerical examples. Okay, so uniform approximation, it is also known as the Chebyshev approximation. What we do, we try to minimize the maximum deviation of the approximation from the original function. So this name Chebyshev approximation it's actually to honor P.L. Chebyshev. He dedicated years of his life to study this problem. So on your right hand side, we have the general formulation for a uniform approximation problem. So f of t is the original function that we try to approximate. It is a univariate function. And then we have psi of at, which is our approximation. And t's are the same t as in f of t, and capital A consists of the parameters that we can change. So basically we are looking for this set of parameters which could give us as best as possible approximation in the uniform sense. So we try to reduce or minimize the worst error in our approximation. So if I try to expand this formulation a little bit for a polynomial and for a piecewise polynomial, this is what it looks like. So f of t is the original function again, and we have our approximation, and ai's are the coefficients, and indeed they are the parameters that we try to optimize. And GITs, they are the basis functions. And for polynomials, these GITs, so the basis functions, they are just monomials. And for piecewise polynomials, these basis functions are constructed based on the truncated power function. Okay, so we have polynomial approximation. It is simple and easy to handle. But when it comes to approximating an unsmooth or an unlibgit function, polynomial approximation is not very efficient. So we might probably need a higher degree polynomial, but eventually it may lead us to numerical instabilities. And one way to overcome this problem is to use polynomial splines. So they are the piecewise polynomials. And this polynomial splines are efficient if we know where to locate the knot. So this knot is the location where we change from one polynomial to another. So if we know the location of these nodes, then it's all good. The problem is convex, and we can use convex optimization techniques to solve the problem. But if we don't know the location of these nodes, then problem becomes non-convex and it is very hard to solve. And even in 1996, Nuremberger and 3 other mathematicians identified this problem as a very hard but still open, important problem in approximation. So rational approximation actually comes to play as a promising alternative to free node spline approximations. And we have theoretical studies which says that rational functions and free node spline approximations are closely related to each other. But these results are developed for non-uniform norms. For uniform norm, it still remains an open problem. Now moving on to the generalized uniform rational approximation. So things are a little bit complicated here. So we try to approximate the function f of t using a ratio of linear forms. So we have linear functions in the numerator and in the denominator, and they are linear with respect to its parameters. So capital A consists of the parameters coming from the numerator, and capital B consists of the parameters coming from the denominator, and these parameters, they are the decision variables for our program. And GT and HT, they are the basis functions. So they are not restricted to monomials now. They can be any function of t as long as this numerator and denominator remains linear with respect to its parameters. And of course, we need our denominator to be positive, and we usually fix one of the terms in the denominator to avoid getting multiple optimum solutions which are multipliers of each other. So for an example, if capital A and capital B, if they are an optimum solution for one particular problem, and if we multiply capital A and B by a constant alpha, then alpha A and alpha B will also be optimum solution for the same particular problem. So in order to avoid getting these confusions, we usually fix one of the terms in the denominator. So this term, generalized rational functions, it was introduced by Henry L. Loeb and E.W. Cheney in 1964. So when I say generalized rational functions, it is actually in the sense of this paper introduced by Henry and Cheney in 1964. Because for some people, when we say generalized rational functions, it may probably mean something else. But for us, when I say generalized rational functions, I am actually talking about a ratio consists of linear functions. So we have linear functions in the numerator and another linear function in the denominator, but they are linear with respect to its parameters. So one very well-known example for the generalized rational approximation is this classical case. So we use two polynomials as the ratio, one polynomial in the numerator and another polynomial in the denominator. So basis functions are now just monomials. We have monomial basis functions for numerator and denominator. And the set of parameters, so we have n plus 1 parameters coming from the numerator and m number of parameters coming from the denominator, since b0 will be fixed. So altogether we have n plus 1 plus m number of parameters as the dimension. So when we usually, when we say rational functions, we are actually talking about a ratio of two polynomials. But because we will be now using generalized rational functions as well, therefore, in order to avoid the confusions, I will refer to just rational approximations as classical case. And for the other type where we use ratio of linear functions, I will refer them to as generalized uniform rational functions. So this is a comparison between rational functions and polynomial approximations. So in the figure on your left, we have three functions. The blue color function is the original function that we try to approximate. It is a nonlinear and a non-Lipschitz function, and it has a sudden change at 0.25. And the black color function is the rational type 4, which means we try to approximate this function using a ratio of two polynomials. And the degree of the numerator is 4 and the degree of the denominator is 4. So altogether, we have 4 plus 1 parameters coming from the numerator and 4 parameters coming from the denominator. So the dimension is 9. And this pink color function, it is the polynomial approximation of degree 8. So we have 9 parameters in total. So for this rational type 4 and polynomial degree 8, for both of these approximations, the dimensions are the same. Dimensions is 9. So the rational approximation is very accurate and it is very, very close to the original function. But polynomial approximation, it cannot even catch this abrupt change in the original function. If we move to the right-hand side, we have the maximum deviation graphs. So the maximum deviation for the polynomial approximation is almost 3 times bigger than the maximum deviation for the rational type 4 approximation. So when it comes to approximating nonlinear or a non-Lipschitz function, it is probably a good idea to use rational functions over polynomials, because we will get superior results over polynomials if we use rational functions. And this is a comparison between classical rational approximations and generalized rational approximations. So the figure on your left, we have 3 functions again. The black color function is the original function that we used before. And the blue color function is rational type 4, which is the same as before. So this pink color function is rational piecewise 2, which means now we have a generalized rational approximation problem. We have a generalized rational function. This rational function consists of piecewise polynomials of degree 2, one in the numerator and another one in the denominator. So we have 9 parameters coming from this problem. I will talk about this, the dimension and everything about this approximation when I move to numerical experiments. But for now, we have 9 parameters here. And for the rational type 4 as well, we have 9 parameters in total. But for these piecewise polynomials, we fix the knots and we optimize the coefficients. So we fix both knots in the numerator and in the denominator. We fix them at 0.25. So for this case, we know what our basis functions are and we know where to locate our knots. So we get a superior result, or the rational approximation. And if we move to the right-hand side, we have the maximum deviation graph. So the maximum deviation for the rational approximation, where we use a ratio of 2 polynomials, it's almost 0.06. But for the rational piecewise approximation, it is somewhere around 0.01. So if we know what basis functions we should use, and if we know where we should locate these nodes exactly, then it is highly likely to get an accurate approximation rather than using classical rational functions. So we have the linear inequality method. It was introduced by Henry L. Loeb in 1960. So this is one of the oldest but simplest method developed for rational approximation in uniform norm. So at that time, they called this a ratio of linear forms. And few years later, in 1964, then only they came up with this terminology, generalized rational functions. So before that, they called this ratio a ratio of linear forms. So what they do in this linear inequality method, they take the generalized rational approximation problem, and then they take the variable z to be the maximum deviation, and then they come up with these inequalities. So if we include z into our decision variable z, these inequalities become nonlinear. So what they did, they identify the upper and lower bounds for this set, and then they fix set at the midpoint of this interval. And then they wanted to check if this system of inequalities has a feasible solution. And according to the feasibility, they update the upper or the lower bounds. So at each step of this process, they have to check if there is a feasible solution for this inequality set. So the way to check if there is a feasible solution or not, it was done by solving a linear programming problem. So at each step, they fix set at the midpoint of the interval, then they solve the linear programming problem to check the feasibility of the original problem. And then according to the feasibility, they update the upper and lower bounds. So at that time, they probably did not realize that the objective function of this generalized rational approximation problem defines a quasi-convex function. But now it is very clear, so there is no surprise that this method works this very well. So quasi-convex functions, they are even more general type of functions than convex functions. So, and there are different equivalent definitions on how to define a quasi-convex function. So we say that a function is quasi-convex if its domain and its all sublevel sets are convex sets. So for an example, for univariate case, any monotonic function is quasi-convex. So basically logarithmic function, exponential function, they are quasi-convex functions. So in 1973, Ian Barrodale showed that the classical rational approximation problem where we construct approximations using a ratio of polynomials, he showed that it defines a strictly quasi-convex function, but for the generalized rational approximation problem, it defines a quasi-convex function. So we use this fact of the quasi-convexity of this problem to develop the bisection method for this generalized rational approximation problem. So this is the proof for the quasi-convexity of the problem. So we take the objective function f of a, b, and t, and we define this ratio to be r of a, b, and t. So we have this ratio, and ATGT, the numerator is a linear function, and it is linear with respect to capital A. And we have the denominator, and it is linear with respect to b, its parameters. So basically, we have a ratio of two linear functions. So, or we can say a ratio of two affine functions. So if we have a ratio of two linear functions, then the ratio is a quasi-linear function, which means this this ratio is quasi-convex and quasi-concave at the same time. So this ratio is quasi-affine or quasi-linear. Then if we rewrite this absolute value function as the maximum between f of t minus r of abt and r of abt minus f of t, then we are basically taking the maximum between two quasi-convex functions, which is quasi-convex. And then ultimately we are taking the maximum of a family of quasi-convex functions, which is quasi-convex. So f of abt, the objective function, defines a quasi-convex function.
Vinesha, so,
Yeah.
excuse me, just a very naive question. Looking at this theorem and the definition of the function f capital, which is the maximum over t, it shouldn't depend on t anymore, or I probably don't understand something. You're already taking a maximum over t. T disappears.
Mm-hmm.
How do you say that it still depends on t?
No, t is just a parameter. So
Yeah.
only a and b are decision variables.
So f capital doesn't depend on t, right?
No, t is the
No.
parameter, just a parameter.
Mm-hmm.
But we've already taken maximum over t.
Yeah,
In the definition.
that's right. No. We just want to show, well, probably not very good to list it as, it really looks like it's a variable, but it is a parameter because we'll take maximum of weight. So that's correct. We just want to show that T is present here because people get confused. There is T,
I got confused.
Okay, so you got confused, but another way, because we were presenting that way and people were confused, we changed this way. Now the other group is confused, but I think you are right. So technically, because it's not a variable, so we shouldn't actually put it here. It is a
So
parameter.
it is meant to be a point, the value of T where maximum is attained.
That's right. Yes.
Okay, thank you. But again, how does it depend on T?
No, it doesn't depend on T. It depends on T only in the sense that it's a parameter. So we want to keep it for the reference. It's not a variable.
Okay,
Because,
I'm not sure I understand, but I don't want to take much time. Thank you.
Okay, may I just interfere that I also think that T shouldn't be here. So I think it will be easier for everybody to just think that it's big F of AB and there's no T there.
So I'm not the only one confused. Okay.
Yeah, maybe it's a good idea to remove T from F of ABT. Yeah.
Yeah, so there's just this value of T at which the maximum is attained, and it somehow made it to some other formulas, I think. Yeah, so yeah, let's just continue. I think we have cleared that.
Yeah, go ahead, Vinesha.
Yeah, okay. Okay, so we have this lemma now. If the approximation is quasi-linear with respect to its parameters, then the corresponding Chebyshev approximation problem is quasi-convex. So this is actually extending the linear inequality method to a broader class of functions, which is quasi-convex. So the proof of this lemma is straightforward. It is not very different to the previous proof. So instead of taking a ratio of linear functions, now we take a quasi-linear function. So f of at is a quasi-linear function with respect to capital A. And then if we rewrite the absolute value function as the maximum between f of t minus capital F and capital F minus ft, then we are taking the maximum between two quasi-convex functions. And then ultimately we are taking the maximum over a family of quasi-convex functions, which is quasi-convex. So moving on to the bisection method developed for quasi-convex optimization. So here we are working with the representation of sublevel sets, and this method relies on solving a convex feasibility problem at each step of this bisection method. And if this, sorry, one moment. So if this problem is feasible, then we update the upper bound, or else we update the lower bound. So luckily for the case where we use classical and generalized rational approximations, this convex feasibility problem can be reduced to solving a linear programming problem. So before I move on to the bisection algorithm, I have to reformulate my problem a little bit. So I take the maximum deviation to be this variable Z, and since the denominator is positive, we can multiply each term by the denominator. So the direction of this inequality will not change. And then we take everything on our right-hand side to the left-hand side. So we come up with this problem. And I would like to call this problem problem 1, because I will be referring to this problem again in the next 2 slides. So now if we include Z into our decision variable Z, these inequalities become nonlinear. So what we do, we specify the upper and lower estimates for the bisection interval. Then we fix Z at the midpoint of this interval. And then we have to check the feasibility of problem 1. if there is a feasible solution, then we update the upper bound, or else we update the lower bound. And we have to continue this process until the gap between these two bounds become really very small. So the next natural question that comes to mind is, how do we check the feasibility of problem 1? So we check the feasibility of problem 1 through the convex feasibility problem. So it is not easy to formulate the convex feasibility problem, but for this case, we know how to formulate the convex feasibility problem, and therefore we can solve it. So for this classical rational approximation and for the generalized rational approximation, this convex feasibility problem is reduced to a linear programming problem. So what we do, we solve this problem 2, we check the value of u, and if u is less than or equals to 0, then problem 1 is feasible. If u is greater than 0, then problem 1 is infeasible. So according to the feasibility of problem 1, we update the upper and lower bounds. So this is how the bisection method works. And this is identical to the linear inequality method, which was developed in 1960. So at that time, they didn't realize the quasi-convexity of this problem, but now we know, and there is a clear correspondence. They are identical methods. Now we want to check if we can extend these results for approximations in the form of a general quasi-linear function. So we take a quasi-linear function f of at, and the feasibility problem, so since f of at is a quasi-linear function, so the feasibility problem described by these inequalities, they are convex sets. So f of at is quasi-linear, therefore we are working with sublevel sets here. So even though you see just 2 inequalities, we have this type of inequalities for each t in this interval CD. So we have a set of constraints and they are convex sets. So basically we have to check if we can find a point in the intersection of these convex sets. Okay, so now we are moving on to the numerical experiments. So this first experiment is a free not linear approximation. So I have to mention that the coefficients are fixed. So we were discussing about another example earlier where we fix the knot and optimize the coefficients. But at this example, we are fixing the coefficients and optimizing the knot value. So A0, A1, and A2, they are the coefficients and they are fixed. And theta is our only variable and it is subjected to optimize. And we want A2 to be non-zero. If A2 is 0, then we end up with this linear piece and there is nothing to optimize. So we need A2 to be non-zero. And this is kind of an example where the feasibility problem is not at least straightforward to see which linear programming problem that we should solve. So if I take the maximum deviation to be delta, then we come up with these 2 inequalities. And if I simplify this further and further, and if we take ft minus a0 minus a1t to be the function g of t, and delta divided by the absolute value of a2 to be the variable set, then we come up with these 2 inequalities. So now the feasibility problem is equivalent to fitting this maximum function in the area between gt minus z and gt plus z. So we want to check if there is any theta value that could fit this maximum function between these 2 bounds. So we consider 2 cases here. So the first case is more than one solution. So this upper green color function is the gt plus z and the lower green color function is gt minus z. And in between we have the function gt, which is red. So what we do, we start at 0 and then we go all the way down until we hit the the lower bound GT minus Z, and then we go up because this maximum between 0 and t minus theta, this function consists of two linear pieces. So for the first piece, it's 0, and then it goes up and the slope is 1. So what we do, we start at 0, we go all the way down until we hit the lower bound, and then we go up. So for this case, we have more than one possibility for theta. So theta can be anywhere between A and B. And for any theta value between A and B, the problem will give us a feasible solution. So in this case, again, we start at 0 and we go all the way down until we hit the lower bound, and then the slope is 1, so we go up. But for this case, there is no feasible solution. There is no theta value which satisfy the conditions in our problem. So this is another set of examples. We are using ratio of piecewise polynomials, but now the knots are fixed. So for the previous case, we fix the coefficients and we move the knot, but here we fix the knots and we optimize the coefficients. So, so we have 5 parameters coming from the numerator and 4 parameters coming from the denominator, and the B naught is fixed. Therefore, altogether we have 9 parameters in total. So we have different basis functions here now. So we have monomials for the first few terms, the basis functions are monomials, and for the next few terms, the basis functions are these maximum functions. And we have two different theta values, theta 1 and theta 2. Theta 1 belongs to the numerator and theta 2 belongs to the denominator. So even in here, we consider two sets of examples. In the first set, we fix both of these knots at the same point. And for the second set, we fix these two knots at different places. So this is when we fix both knots at 0.25. So we know that this original function has this abrupt change at 0.25. It has this sudden change at 0.25. So we fix both knots, one in the numerator and the other one in the denominator. They both are fixed at 0.25. And approximation is very, very accurate and very, very close to the original function. And if we move to the maximum deviation graph, sorry, we have 9 alternating points. And the maximum deviation is somewhere around 0.01. Now, if we move this knot a little bit further to the right-hand side, so we locate both knots at 0.5, we get only 8 alternating points, and the maximum deviation is somewhere around 0.1, which is much higher than before. Earlier we had the maximum deviation of 0.01, but this time it is 0.1. And now we move this knot to the left hand side, so this both knots are located at 0, and we only get 6 alternating points. And the maximum deviation is slightly lower than 0.1. And now we move this knot even more further. So both knots are located at minus 0.5. And we only get 9 alternating points. And we have this peak here, which is ready to come down. So if we reduce the precision variable of the bisection algorithm, we might probably get more than 7 alternating points. So now we fix these two knots at different locations. So for the first two, we fix the knot in the numerator at 0.25, which is the exactly this changing from one polynomial to another happen. And for the next two approximations, we fix the knot of the denominator at 0.25. And for the next two experiments, neither of these two knots are located at 0.25. They are located at different places. And for the last two experiments, these knots are actually located at equidistant knots. So for the first one, we have located the knot in the numerator at -1/3, and the knot in the denominator is located at 1/3. And then for the last experiment, we interchange these two knot values. Okay, so this is the first case. The knot in the numerator is at 0.25, and the knot in the denominator is at 0.5. So we only get 7 alternating points, and the maximum deviation is slightly less than 0.06. And if we keep the knot in the numerator at the same place where the correctly identified knot point, and if we move the knot in the denominator to 0, we get 7 alternating points. But here again we have this peak ready to go up, this peak ready to go down. So hopefully if we reduce the precision variable of the bisection algorithm, we may probably get more than 7 alternating points. And now if we fix the knot in the denominator at 0.25, and if we move the knot in the numerator to 0.5, we only get 5 alternating points. And if we even move this knot 1 further to 0, we only get 7 alternating points. But again, we have another peak here which is ready to come down, and the maximum deviation is not very different. It is somewhere around 0.06 for both cases. And now we locate these two knots at different places. So the knot in the numerator is at 0.5 and the knot in the denominator is at 0. But we still get 6 alternating points. And if we interchange these two knots, we get 7 alternating points. But the maximum deviation is not very different. For the first case, it is somewhere around 0.06. And even for the second case, it is the same. So now we fix our knots at equidistant locations. So so the knot in the numerator is located at -1/3, and the knot in the denominator is at 1/3. We get 7 alternating points, and the maximum deviation is slightly bigger than 0.06. But if we interchange these two knots, we get 9 alternating points, but the maximum deviation is it remains the same. For the previous case, it's slightly bigger than 0.06, and for this case as well. So now you may be thinking that if we introduce more knots, if we introduce more equidistant knots to this function, we may probably get much accurate approximations. So that is why we wanted to reduce the degree of these two piecewise polynomials, and we introduce more knots. So the degree for the numerator piecewise polynomial is 1, and degree for the denominator polynomial is 1. And now we have introduced more knots. We have 3 different knots for the numerator and 3 different knots for the denominator. So it doesn't matter if θ1 is equals to θ4, that's fine. But if θ1 is equals to θ2, then we can add these A2 and A3 terms together. Therefore, it is really very necessary to have different knot values for θ1, θ2, and θ3. So for the first case, we have 4 intervals and 3 different knots. So θ1, 2, and 3, they are located at -0.5, 0, and 0.5. And θ4, 5, and 6, they are again at -0.5, 0, and 0.5. So if you look at the approximation, we can see very rigid pieces of functions as the approximations, and we only get 4 alternating points. And the maximum deviation is somewhere around 0.25. But if we introduce more different nodes, if we have 5 intervals and 4 different nodes, we get 6 alternating points. But the maximum deviation is now reduced. It is somewhere between 0.1 and 0.15. So now you might think that if we introduce more different nodes, we will get a better approximation. So now we introduce 7 intervals. We have 6 different nodes. So each of these nodes are located at different places, but we only get 3 alternating points, and the maximum deviation is about 0.3. It's probably more than 0.3. So the conclusion of these numerical experiments is that if we know which basis functions that we should use in our approximations, and if when we use piecewise polynomial approximations, if we know the exact location of the nodes, then it is highly likely to get a nice and accurate approximation. So to summarize everything, a uniform rational approximation problem where we use a ratio of polynomials, it defines a strictly quasi-convex function, and the basis functions are monomials for that case. But when we have a ratio of linear forms, the generalized rational approximation problem, it defines a quasi-convex function. So the linear inequality method, it is identical to the bisection method applied to generalized uniform rational approximation problem. And the feasibility problem is not only convex, but even linear. So it is, even though this method relies on solving a convex feasibility problem, for this particular case, for generalized case, it is even easier for us. We have to solve a linear programming problem. So this observation leads to an extension of linear inequality method to a broader class of function, which is quasi-convex. And as the future work, we hope to consider other type of methods developed for quasi-convex optimization to identify if there is any correspondence between these methods. And we will also be considering multivariate approximations as well. So thank you everyone for your attention.
Thank you, Vinesha. Very nice presentation.
Thank you.
With good voice and everything. So questions, please, the audience. We have huge audience of 10 people. Please ask questions.
Hello. Well, first of all, thank you for the very nice talk. I want to make some comments, namely that the problem you are considering belongs to a class of problems called generalized fractional programming. I will tell you what it means. Fractional programming is just minimizing or maximizing the ratio of two functions with suitable properties. And generalized fractional programming means, for instance, minimizing the maximum of a finite number of quotients. Okay, then this was studied very much, maybe some 30, 40 years ago. And there is, even they made experiments about which algorithms perform better for such kinds of problems. And if I remember well, the conclusion was that a combination of an extension of Dinkelbach method. Dinkelbach method is a method for ordinary fractional programming, just one ratio, but there are extensions to the generalized case. Then there was a combination, if I remember well, of Dinkelbach with Newton. This was the algorithm which performed the best. So it would be nice to compare what you have obtained with those classical methods. But in the opposite direction, you are just dealing with a very special case of generalized fractional programming. So maybe your method can be used for general problems, not just for a rational approximation. I even contributed to the topic with an algorithm some 30 years ago, in 1990 or the early 19s, I don't remember exactly, in a paper published in JOTA. And my algorithm was very interesting. I still don't understand it. I mean, not the algorithm. The algorithm, I understand it quite well because but I don't understand its performance, because it happened that when you have just one constraint, our method, I said our because it was a joint work with a former student of mine, then our method was the best of all. But if you had more than one constraint, just two constraints, it was the worst of all. Okay, and this is impossible to understand because it was a cutting plane method. So in a cutting plane method, you are adding constraints as you iterate. Okay, so what was a good method when you had one constraint should immediately become a bad method after one iteration because you already got two constraints. But it seems it didn't notice that it has added one constraint. Okay, well, these are just a few comments. Maybe you can extend your method to more general problems and also compare your results with those classical results in the literature. Okay. Again, thank you for the nice talk.
Thank you, Ari. Thank you for the comment. Yeah.
So can I also step in? So Juan Enrique, thank you very much for your comment. Actually, I think the work you are talking about, so we also found it's from, I think, 1987. So the work by Jean-Pierre and some of his co-authors, Jean-Pierre Crouzet.
Yes.
So he actually, let's say, for a rational approximation, so one of the most best performing methods, it's so-called differential correction method. And they have differential correction 1, 2, 3. So, and the method you were talking about, it actually corresponds to differential correction 1. And then when they included Newton method, it became differential correction 2. But of course, at the time when the method of differential correction was developed, they didn't know about it. So I think what Vinesha is trying to do, she is trying to connect these two areas, because rational approximation is exactly where we have the overlapping. So she is trying to actually connect these two areas so they can benefit from each other. I think that's what she's trying to do. And it's just extremely fascinating how it works. And we will probably look at your method as well. So maybe we will actually understand later on so why sometimes it's the best, sometimes it's the worst. But it was really very interesting because basically one area was feeding another one to get, let's say, inspiration for improvement, and it worked. So
yeah. So I know that, I see that you know very well, I mean, the work by Jean-Pierre. I learned this topic from him. I remember there was a paper, Crouzet, Ferland, Scheibel.
Yes, that's correct, this paper.
It was the classical paper, but they were interested in theoretical aspects rather than algorithms, although they... regarding my my algorithm, it was really very strange. And I remember it was an application of a method by Plastri, a general method by Plastri, a Belgian mathematician. And I didn't understand what happened with our application to this particular kind of problem. And I wrote to Plastri. By the way, I never met him, but I wrote him a letter. In those times, there was no email. And he wrote me a very long letter trying to explain the strange behavior. But so my advice, Nadia, is please don't look at my method, okay?
No, I think because we are also looking at extension to multivariate case. So because the method Vinesha was presenting, it's the oldest one and the simplest one, it's really straightforward to extend it to multivariate, while differential correction or Jean-Pierre's method, and probably yours, is not so straightforward to extend to multivariate case. So that's why we're trying to start from, something simple and then building up on the top of it.
Okay. Thank you, Nadia.
Yeah, thank you very much.
You're welcome.
So we've had some good discussion, possibly with good outcomes. Any more questions, comments? Who else wants to start a discussion? Nadia wants to start a discussion.
Can I ask a question to Vinesha? So, Vinesha, in your opinion, so do you think we will succeed with multivariate approximation, or do you think there are some difficulties here? So, what is your opinion about the future of this research direction?
I think it might work for multivariate functions, because even if we have a flat area, so bisection method will work. So even when we move to multivariate functions, we have multiple variables. So I think it might work, but it might probably not be very efficient as this case. It might be computationally complex, but it might work. Yeah.
Okay, thanks.
So cautiously optimistic opinion.
Yeah, cautiously optimistic.
Okay. Any more comments, remarks, questions? Serenia?
Vinesha, your algorithms works when you are working on the interval, in the whole interval AB. I mean, T belongs to the interval. It can be extended to any convex, convex, not compact set instead of the intervals.
This is what Nadia was talking about, multivariate.
Yeah.
No, not multivariate. Is considered instead that T belongs to the interval AB, another compact set. The same function, the same variational inequality, the same rational approximation, only to polynomial P over Q, but instead of the interval, you consider any compact set.
But still in R. Or
Yeah, still in R. Yeah, still in R. Maybe the intersection of two different compact sets or
union of intervals.
Union of
intervals.
Good question.
how meaningful is it? It is just probably separate approximations on separate intervals.
Probably.
Yeah, but
and then we take, yeah.
But consider the same polynomials, not different in each interval.
Ah, okay.
Okay, so there is something to think about.
I think it will
Yeah.
work.
Yeah.
The short question is yes.
Optimistic opinion, not cautiously, optimistic.
Yes. Should answer.
More? If no more, I share what's on the screen. Thank you, Vinesha, for your presentation. Thanks to the audience for coming here. And we see all of you next week on Wednesday.
Thank you, Alex.
Thanks
Thank you,
very much.
Alex. Thank you very much for coming.
Bye.
Yes, Juan Enrique.
I have a request to the organizers.